Now let's put that all together to find some multiple zeros. If x equals alpha is a zero of multiplicity m of your original polynomial, then that same spot will be a zero of multiplicity m minus 1 of the first derivative. Now, let's consider a zero with multiplicity 1, so just a single zero of our original polynomial. It would have a zero of multiplicity 1 minus 1, in other words, 0, in p dash x. Now, what would that look like? Well, if I looked here at p dash x, and if m minus 1 was actually 0, then this whole part would be something to the power of 0. It would be 1, wouldn't it? And I'd have to say that p dash x was just equal to r of x, which remember we defined as just some polynomial. Now, does that make x minus alpha a factor? It doesn't, does it? Because you don't have any of them in there. If you've raised it to the power of 0, then it's effectively gone, right? So this makes a lot of sense. If multiplicity is 2, in other words, we've got a double zero, a double root in our original polynomial, then we should find that we've got a single root in the first derivative, and so on. But it does actually work when multiplicity is equal to 1, as long as you get your head around it. Now, you can use this rule again and again with higher derivatives, so you can keep on differentiating, and you'll find that it will keep on going down, m minus 2, m minus 3. Let's have a look at how that works. It basically works because when we differentiate p of x and we get p dash x, we get something that's got the same sort of format. We've got some x minus alphas to a power multiplied by some other polynomial that we've proved is not 0. So it's a legitimate factor. And this keeps on happening. So if we differentiate again and find p double dash x, then what we get is 2 bits. We get the same factor but raised to m minus 2 now, multiplied again by some other polynomial. And it keeps on happening. So how we're going to use this? Well, this blue box is important. It tells us how we can use this in a nutshell. Once we find a 0 of our original polynomial at some value, let's say x equals alpha, and we do that with our calculator hack just by trying some low integers, we can differentiate our polynomial, so find p dash x, and then we can sub our 0 into that first derivative. And if it equals 0, then we found that our original 0 must be at least a double 0. Okay, now that makes sense because if it was a double 0 here and this was a 2, then what we'd find is that the next version down, the derivative, it's a factor with a multiplicity of 1. Now we can keep on going. So it doesn't mean it's necessarily a double 0. It means it's at least a double 0, double or higher. So then you can differentiate again if it's easy and practical to do so. Find p double dash x and sub your 0 into that. And if that's equal to 0, then you know that your original 0 wasn't just a double, it must be a triple or greater, and so on and so on. Now, it makes sense that you're going to look at the highest power of x in your polynomial to know when to stop. And you're going to combine this skill with the rest of your little menu for factorizing. So the full factorizing menu that we have now for polynomials has now got a new step, and we've put it in there right under the first step. Our first step, remember, was to test whether some low positive and negative integers would be zeros, and we used that calculator hack. Remember, we typed in the whole polynomial, but we used the red A button anywhere that there was an x. So we're letting the x's basically equal big A. Now, we found that if we change the value of A, try 1, -1, 2, -2, a few obvious choices first up, if we get 0, then that value of A, or that value that you've used for x, basically, is a 0 of the polynomial. And that means that x minus whatever that was is a factor. Now, you could start using that, and remember we're making sensible choices by looking at the constant term and seeing if the whole polynomial was monic, to try and figure out what would be good choices to make with that calculator hack. And sometimes we can get the whole thing out just with that. Now we've got step 2, which is that we can test any zeros in p dash x, the first derivative, p double dash x. We can even go further and further if we like, to find the multiplicity of the zeros that we've got, because otherwise it can be hard to find whether a certain 0 is actually repeated. We've also got that extra skill. We can use the sums and products of zeros to find more zeros, and once you know a 0, you can do x minus whatever that is to find a factor. And then basically our last resort is that we can multiply the known facts together and divide the entire polynomial by those using long division to find the remaining factors, but we saw that that's time consuming, so that's kind of the last resort. So now an example, we need to factorize this polynomial. In other words, we want to rewrite it so that it's got a bunch of things in brackets multiplied together. Now, quick inspection here, I can see it's got a coefficient of 1, a leading coefficient of 1, and the constant term is -8. So I'm thinking that the parts in brackets are probably ending with numbers like 1, 2, 4, and 8 because they're factors of 8. So it makes sense that when I try my calculator trick, I'm going to try numbers like 1, 2, 4, and 8, -1, -2, -4, or -8 first. Now let's start with the low ones. I've already loaded this whole thing into my calculator using the red A anywhere that there was an X. Before I did that, I already started by putting 1 in by pressing 1, Shift Store A, so that A is 1 before I start. Then I've put it in. And then remember, we'll hit the up button to go into your calculator, and it will recall that whole string that you've put in just to check that you're in the right place. When you hit equals, it will now use the value of A you most recently put in. And I'm getting a 0 there. So that tells me that P of 1 is 0. Makes sense to try -1, so just type in -1, Shift Store A, and then the up button to go back to your polynomial, hit equals, -108, so that didn't work. Now let's try 2, Shift Store A, now 2 is A, and if I go up again, hit equals, sure enough I can see that P of 2 is also 0. So what that's telling me is that x minus 1 must be a factor with a multiplicity of at least 1, could be greater, and x minus 2 is also a factor. Now, I don't know the multiplicity there, but it makes sense to have a look, because if I multiply these together, I've got +2. And I'm looking for altogether -8, but I also kind of want 5 factors because the degree of this polynomial is 5. So it makes sense now, I think, to probably try 4. So if we try 4 and try -4, and we can see that neither of those are factors, then it makes sense now to have a look and see the multiplicity of these ones. So to do that, we'll find P dash x by differentiating this one term at a time. So see if you can work along with me. We're going to have 5x to the power of 4. We need to bring the 4 down, so we'll have -32x cubed plus 75x squared minus 38x, sorry, minus 76x I should say, plus 28. Okay, now we've got a couple of choices. We can put that whole thing into our calculator as a string, or we could work quickly and easily just to use our numbers to check. So subbing in 1 here should be quite straightforward. I've got 5, and I can just work this out. 5 minus 32 plus 75 minus 76 plus 28. Subbing in x equals 1 was easy, and I got 0. So P dash 1 equals 0. So what does that tell me? It tells me that this 0 here has a multiplicity of at least 2. So I can think up here that this is 2 or more. Now, you wouldn't write 2 or more up there. We're having a go here, and I'm just sort of showing my thinking. Now I can type all this in as a string, or I could go ahead and use 2. I can probably just do it on my calculator using simple things. So I've got 5 times, and I know 2 to the power of 4 is 16. So 5 16s plus 32 times 8. Whoops, it's minus 32 times 8. I beg your pardon. Okay, plus 75 times 2 squared, that's 4, minus 76 times 2, plus 28. It's quite quick and easy, and I can see that the P dash 2 is also equal to 0. So that tells me that this is 2 or more as well. So if I found that their multiplicity is 2 or more, it probably makes sense to go ahead and see if it's greater than that. So let's find the next derivative by differentiating this one. We're going to get 20x cubed minus 332's is 96x squared plus 150x minus 76. So now let's go ahead and sub in 1 to that, which should be quite easy. We just need to do 20 minus 96 plus 150 minus 76, and we get negative 2, so that didn't give us 0. We'll just note that. But we'll try the other one while we're there. I need 20 times 8, just doing 2 cubed in my head, minus 96 times 4, plus 150 times 2, minus 76, and that did give me 0. So what that tells me is that if the second derivative of this is equal to 0, then this one must have a multiplicity of 3 or more. Now, I've written or more up there because I'm just showing my thinking. When we get good at this, you'll look at what it is and then put your correct numbers in straight away. If this is at least 2 and this is at least 3, they can't be any bigger than that, because what I'm looking for is a polynomial of degree 5 altogether. And if I expand this out, I'm going to have x squared here and x cubed there. So multiplying those together, I've already got x to the power of 5, and I can see that I'm basically done. Now, a quick inspection to check that I get the constant term makes sense, but negative 1 squared, the lasts term in this expansion will be 1, so I'll be multiplying just by whatever the lasts are here. And here I'll have minus 2 all cubed, which is going to give me minus 8. So I can see that I've finished factorising, I've found all the factors, both of them had multiplicity of 2 or more, and they weren't too hard to find. Probably that was quicker than finding that these were factors, looking for other factors and not finding them, getting a little bit frustrated. To do it another method, you would have probably had to multiply these two together and then do long division of something with 3 terms in it, dividing that whole thing. And I think you'll agree that probably would have taken longer and been a little more frustrating to do.